Moving on to infrared light, you have to remember that objects with temperatures around room temperature, with Earth-like temperatures, give off light in the far infrared. So if you want to look at far infrared, people glow in it, the ground glows in it, the atmosphere glows in it, even telescopes glow in far infrared light. And so therefore, you can't look at the far infrared from the ground. You're constantly looking through this haze. So to avoid the glow of the Earth and of the atmosphere and of the telescopes themselves, we have to put far infrared telescopes into space, and we need to use liquid helium to cool them off so they're only a few degrees above absolute zero. At that very cold temperature, these telescopes do not glow in the far infrared, and so finally they can see that fog that would cover them on the ground becomes transparent, and you can see very faint objects in the far infrared. Here are two infrared telescopes. The one on the left is the Herschel Space Telescope, which is operating right now, built mostly by the Brits and European space agencies. And the one on the right was a NASA telescope called Spitzer. It has run out of its coolant, and so therefore it's warmed up and it can no longer look in the far infrared. And so there's a very limited amount of astronomy the Spitzer telescope can do anymore. The Herschel telescope is almost out of coolant. It only has a year or two left, and there's no way to refill it. So once it warms up, it's over and it can't look at anything anymore. One of the most common errors that students make when they wonder why we're cooling these things off is they assume that if they were warm, then the heat would destroy the electronics. But that's not true. I mean, the computer that you are watching this mini lecture on is bathed in far infrared light from you, from the electronics inside the computer, from the atmosphere around it, and it's not burning up. So these telescopes would not burn up if we didn't cool them down. It's just that they glow in the far infrared, and we can't see through that glow unless we cool off the telescope so it no longer is glowing. Near-infrared light can make it down to the ground most of the time. The higher you go in the atmosphere, the more of it you can see. So therefore, near-infrared telescopes are often put on mountaintops, such as the telescope on the left, which is the United Kingdom's infrared telescope. It's in Hawaii on top of Mauna Kea. It's above a lot of the atmosphere. It's at 14,000 feet. NASA has a new telescope called the SOFIA infrared telescope, and it rides around on a modified Boeing 747. There's a picture of it here on the right. The 747 takes off and climbs to 40,000 feet, and then they open that door. The door is designed in such a way that the telescope can look out and it doesn't affect the aerodynamics, and the telescope can peek out through that. And by being at 40,000 feet, it's above a lot of the atmosphere, and therefore almost all the infrared light, the near-infrared light, can make it down. We'll now skip over optical light since we've talked about it, and we'll skip ultraviolet light because ultraviolet light can be detected in very much the same way as optical light. The Hubble telescope is very good at detecting ultraviolet light. You can use the same mirrors and very similar detectors, so we'll skip over it as well and move on to X-rays. X-rays come from very hot objects, very hot sources, and one of the most common sources of X-ray light is gas that is heated to millions of degrees. Here on is a picture of something called Stephan's quintet. In this picture there are 5 galaxies, 1, 2, 3, 4, and 5. These 4 galaxies here are all in the process of colliding with each other, smashing in and making one single big galaxy. We'll talk about galaxy collisions toward the end of this course. This galaxy here is it's much closer to us, just happens to lie in the same direction, so it looks like it's part of it, but it's not. If we look in, we're now going to see a picture where we combine this picture, which was taken by Hubble, with a picture from an X-ray telescope. So you can still see all the same optical light, but if you look closely in this region, you see a faint blue glow, whereas in the optical picture there's not much there. In the X-ray picture there's a lot of X-ray glowing from this region. that is the gas that is at the shock where all of these galaxies are colliding. And so it's heating up to millions of degrees and glowing in the X-rays. And if we didn't use X-ray telescopes, we wouldn't know that that gas was there. So this movie is going to show X-ray photons, so photons of X-ray light, hitting an ordinary mirror. If we just put an ordinary mirror like the Hubble Space Telescope into orbit, when X-ray photons would hit it, they would just be absorbed. They don't bounce off. X-rays will only bounce off a mirror if they come in and hit the mirror at a grazing angle, at a very small angle. So we use nested mirrors like this to have the X-rays barely glance off of them and come to a focus at a point far behind the mirrors. So this is on the left is a picture of the Chandra X-ray Observatory, which is currently working and has been up in space for I think 13 or 14 years now. Here at the front of the telescope, these are the mirrors that we saw in the movie. And the light, the X-rays, come to a focus way down here at this end of the telescope. So the X-ray cameras are down here, the mirrors are here, and this tube in between, the tube is here just to hold the camera at the right distance away from the mirrors. So for X-rays, you have to do this very precise bouncing of light. Gamma rays come from the most energetic phenomena in the universe. Mostly from black holes and from supernovae or exploding stars. So gamma rays allow us to look at this, but gamma rays are also the most energetic electromagnetic light, and there are no mirrors in existence that can focus gamma rays. So to study gamma rays, we have to use some very high technology methods. Here is an artist drawing of the Fermi Gamma Ray Observatory. And you see it doesn't look like any other observatory. There's no telescope, there's no mirror. It just looks like a big box flying out in space. The top part of this box, this black region here, is actually a series of very closely spaced plates. And when a gamma ray photon comes in, it hits the metal and it changes into electrons. So these electrons that are in the atoms absorb the gamma rays and then shoot off at really high speeds, almost the speed of light. And these electrons come down and pass through a series of smaller electrically charged plates. When they hit one of these plates of metal down here, they send a signal to a computer. And the computer can figure out where the electron went, what its path was, and it can trace it backwards to find out where in the sky the gamma ray came from. Gamma ray observatories have been very useful in exploring some of the largest black holes in the universe, and when we talk about black holes, a lot of the information that we get from them comes from gamma ray telescopes. Let's now summarize what we've learned about non-optical telescopes. Outside of the visible and ultraviolet wavelengths of light, we have to use different types of telescopes because the nature of the wavelengths of light are different. But yet we want to look at these different wavelengths of light because they come from a very wide variety of astrophysical phenomena, things we want to see. So radio telescopes, a single radio telescope cannot see very sharply because radio light spreads out to diffraction. Its resolution is not very good. So we often will join together multiple radio telescopes using a technique called interferometry. Interferometry allows you to see sharper. So if you have a series of radio telescopes that are all spaced 30 miles apart, then they will act like a single telescope that's 30 miles in diameter. When we go to the far infrared, because the entire Earth is glowing in the far infrared, we have to launch telescopes into space. We have to cool these telescopes down to just a few degrees above absolute zero. Otherwise, the telescopes themselves would glow in the infrared, and that would hide astronomical sources. Near-infrared telescopes need to be high on mountains or in airplanes. Otherwise, they work very similar to optical telescopes. X-ray telescopes, if an X-ray telescope had a normal mirror, that mirror would absorb the photons, so we have to use this grazing mirror where the X-rays just come in at a shallow angle and just barely bounce off the mirror and come to a focus far away. Gamma ray telescopes, we have no way of focusing the light, and so we have to use very special technology in order to detect the gamma rays and determine where they came from. This completes the mini lecture on non-optical telescopes. You can now go back to eCollege and complete the response to mini lecture 2.